Hello, ladies and gentlemen. Let's follow up. This is going to be Unit 7, Lesson 1, video number 2. Okay, and the page got cut off when I was making this PDF Smart Notebook file. So we are actually on page 150 of our interactive notebook, and it says at the beginning of that page, consider the equilateral triangle ABC, where BC is equal to A. Here we are right here. And it's equilateral. Therefore, AC is also equal to A. It's equilateral. So this guy here is also equal to A. So AC is equal to A. And AB is also equal to A, since we have an equilateral triangle. Easy enough. Equilateral triangle. Since the triangle is equilateral, I want to find the measure of angle ABC. What I want is this measure of this angle right here. Well, if it's equiangular, all the angles are 60 degrees. What I'm going to do is sketch the median point starting at C down to D. I'm going to label this intersection point D. And we know from our previous discussion about special right triangles that this guy here is also a median, which divides AB into two congruent segments. And therefore, it's 1/2. It splits that side A into halves. So this distance right here is 1/2 A. And that's interesting. So AD and DB both are 1/2 A. These are 1/2 A. And that's property of equilateral triangles when you have that median, and then it's also a perpendicular bisector. So that guy is 90 degrees. Therefore, if ABC is 60, this guy here is going to be 30 because that median also is an angle bisector. So ADC is 90. We have figured that out. And then DCB is going to be 30. So this is going to be what we call a 30, 60, 90 right triangle. And we talked about these 30, 60, 90 degree right triangles. We're going to use the Pythagorean theorem to find the length of the height there, CD, if you will. But you know what we're going to do? We're just going to use the property of equilateral triangles that says the long leg is square root of 3 times the short leg. So therefore, CD is going to be the square root of 3 times 1/2 A, and we're just going to write that as square root of 3 over 2A. And so that's the length of CD. And we could check that to make sure that we could use the Pythagorean theorem, but let's just use the property of 30, 60, 90 right triangle. And when this is called a special right triangle, since it is a 30, 60, 90 right triangle. All righty. And let's see here. So we're going to consider this right triangle RST, where the measure of STR is 60, and RT is going to be 6. And then it is a right triangle RST, so this is going to be our 90 degree angle. Therefore, this guy is 30. So therefore, the measure of TRS is 30. And again, we're talking about a 30, 60, 90 right triangle. And this is going to present some really nice trigonometric ratios. Hence, the reason this example is in Unit 7, Lesson 1. By the properties of 30, 60, 90 right triangles, the small leg, which is 1/2 the hypotenuse, so that rascal is 3. Simplified square roots even, it is 3. So TS is 3. And RS, which is the long leg, we know is square root of 3 times 3. Okay, or it's better to write that as, what the heck? 3 square root of 3, because this notation is confusing, okay? So now we're simply going to use the definitions of trigonometric ratios, and we're going to find the sine of r. The sine of r is going to be what? The sine of r is the opposite over hypotenuse. Here we have 3 over 6, which is 1/2. The cosine of r is the adjacent over the hypotenuse, which in this case it's 3 square root of 3 over 6, and that's going to be square root of 3 over 2. The tangent of r is going to be the opposite over the adjacent, which is going to be 3 over 3 square root of 3, which is 1 over square root of 3, and I'm going to multiply square root of 3, square root of 3, so this is going to be square root of 3 over 3. Okay. Upon further investigating, there's a typo here in my notes. Got these angles mixed up there. So TRS is 30, and this guy here is 60. So that's going to be your 60-degree angle in your equilateral triangle. So you need to, is there another place, another, no, everywhere else it's good. So the only error I had was right here. The angle of STR was 60, was just a labeling thing here, right there. Okay, and so let's continue and let's find the sine of t. The sine of t is going to be the opposite, which is 3 square root of 3, over the hypotenuse, which is 6, which is square root of 3 over 2. The cosine of t is the adjacent over the hypotenuse, which is 3 over 6, which is 1/2. And the tangent of t is going to be the opposite, which is 3 square root of 3 over 3, which is just square root of 3. Okay? So easy enough. Let's go to the next page, and keep in mind this stuff here was supposed to be on the next page. I'm going to go right to the next page. I have that copied down. So now we are on page 151. We're on page 151. Alrighty, page 151. I have triangle ABC where the measure of angle B is 90. Got it right there, where AB is equal to BC. Right there we go. These things are congruent. Example number 1, let AB equal 5. So I have 5. If AB is equal to BC, then this guy is 5 as well. So I've got BC is equal, it's 5, not B, silly. So this guy is equal to 5. So this guy here is 5. And AC. I could use the Pythagorean theorem, or I can realize that this is a 45, 90 right triangle. The hypotenuse is square root of 2 times a leg. So AC here is 5 square root of 2. This guy here is 5 square root of 2. All right, and the measure of angle A, both of these guys here are 45 degrees. Okay, jump down here. ABC is called a 45, 90 triangle. It's a special right triangle. And let's look at the trigonometric ratios of angle A. So the sine of angle A is going to be the opposite over the hypotenuse, which is going to be 5 over 5 square root of 2. This is going to be 1 over square root of 2, and I'm going to simplify that. Square root of 2 over square root of 2, and that's going to be square root of 2 over 2. Okay? Hey, guess what? The cosine of A is going to be exactly the same, square root of 2 over 2. The tangent of A is going to be 5 over 5, which is 1. The sine of C is going to be the same. Well, the sine of C is also opposite over hypotenuse, 5 over square root of 2. We already know that simplifies to square root of 2 over 2. The cosine of C is going to be the same thing. And the tangent of C is also going to be 1. So those are very, very interesting trigonometric ratios. And if I jump down here to same triangle before, but AB is equal to K, same triangle. But now I have this guy is K, this guy is K. This is going to be K square root of 2 because it's a 45, 45, 90 again. And look at this. Both of these are 45, 45. BC is equal to K. AC is equal to K square root of 2. And if you do the math here, look at the sine of A, which is going to be the opposite, which is K, over the hypotenuse, which is K square root of 2. Guess what that ends up being? Square root of 2 over 2. Hey, guess what the cosine of A is going to be? Square root of 2 over 2. Guess what the sine of A is going to be? 1. And what I would ask that you do I would take very good notes on this particular page. You're going to use this particular page, this example right here, most often. Let's jump to the next page and let's do the last example. There's a lot, sure is a lot going on here. And so let's see here. We have consider the right triangle RST. This is certainly 90 degrees here. Let's label that in something other than yellow. That's 90 degrees. Where RTS is 60, yeah. Therefore, this guy is going to be 30. RT is equal to 1. TS is certainly going to be 1/2 because this is a 30, 60, 90 right triangle. Short leg is 1/2 the hypotenuse. TRS is going to be 30. Well, I don't even need to use simplified square root. I know that TS is equal to 1/2. And I know that RS, which is going to be the square root of 3 times short leg, RS is just going to be square root of 3 over 2. Hey, what's the sine of R? The sine of R is going to be the opposite of R, which is 1/2 over 1. Hey, guess what? That's 1/2. The cosine of R is going to be the square root of 3 over 2, adjacent side divided by 1. Hey, guess what? That's just square root of 3 over 2. The tangent of R is going to be 1/2 over square root of 3 over 2. And I'm going to multiply top and bottom by 2. That's going to be 1 over square root of 3. I'm going to simplify that. Square root of 3 over square root of 3, and that's going to be square root of 3 over 3. That's the tangent of R. Hey, let's look at the sine of t. The sine of t is going to be, the sine of t is going to be square root of 3 over 2. What's it going to be, though? It's going to be square root of 3 over 2 divided by 1, which is square root of 3 over 2. The cosine of t is going to be the adjacent to t over 1, which is just 1/2. And the sine of t is, or the tangent of t is going to be opposite, square root of 3 over 2, divided by 1/2. The 2's cancel, square root of 3. So this also is a very, very, very important example. Please write that down. This is going to pretty much finish the notes for lesson 1. You will have activity of lesson 1 as well to do.